Oh, wait. Oh, yeah, there is.
All right, so return to see. You can't say that unless it's back in the chat.
Okay, maybe we can get started. So, ready? Okay, so let me just start by reminding you of this theorem that we proved last time, that if you have any combinatorial Hopf algebra, then we have a unique morphism from it to the terminal one, which is QSYM with the character Sara Q. Now remember, the setup is that H is supposed to be a Hopf algebra that is one of the ones that we like. It's, it's labeled by combinatorial things usually. It's graded and it's connected, and the graded pieces are finite dimensional. And alpha is just any multiplicative function, any character. And this theorem gives us a recipe, and we actually gave explicitly the recipe last time. Given an element of the Hopf algebra, you get a quasi-symmetric function for free. Okay? So for example, we carried this out last time, and we saw how. Okay, so before I say that, let me say that if H is co-commutative, then I have a unique morphism to actually symmetric functions. Okay. And this was very explicit. And for example, we saw that if H is the Hopf algebra of graphs, and let me say the co-commutative, because we've seen two of them. One is co-commutative and the other one is not. Then this gives me this one gives me a recipe that for every graph I get a symmetric function. Okay? And we said that this symmetric function is called the chromatic symmetric function. Stanley first constructed this. And the point is that if you look at it from this point of view, then this is not a clever construction. This is just an inevitable consequence of having this universal theorem, that once you fix your Hopf algebra and you fix your character, in this case the character was, maybe I should write it down. So remember that the character here was 1 if G has no edges and 0 otherwise. And then this maps a graph G to xg, which is Stanley's chromatic symmetric function. Okay. So one thing that I want to make clear is that this is just one of many examples, because we have many Hopf algebras like this with characters, and each one of those is going to give us some way of assigning to our combinatorial objects some either symmetric or quasi-symmetric function. Okay. Now, if this course was a lot longer and I had talked to you a lot more about symmetric functions, then you would be immediately very excited about this, because I've hinted at the fact that symmetric functions are a very fundamental object that is very closely related to what's called the representation theory of the symmetric group. And there's whole books about this and whole courses that one could teach about this. And the point is that this gives me a link between questions in graph colorings and the representation theory of the symmetric group. And you immediately ask a lot of questions, and there are some nice theorems that Stanley and others proved. And if I had more time to talk about symmetric functions, then I would tell you more about this connection. Okay? And the same with quasi-symmetric functions. The point is that once you study these two things enough, then you can study any Hopf algebra by sending it over to QSYM or to SYM, and then applying what you know about these guys. Okay? Now, because the class is over today, we're not going to get to do a lot about SYM or QSYM other than what we've done. We've done some stuff, but we could have done much more. So what I want to do today is something a little bit different. We have a recipe to go from any Hopf algebra to these two. Okay? And what I want to do is now take ourselves even further to a different Hopf algebra that we're very familiar with and that is much simpler, which is the Hopf algebra of polynomials in one variable. And this is one of the first ones that we considered. Okay. And so that's the next thing we're going to do. So let me write down a proposition. And the proposition is the following. There is a morphism of Hopf algebras from QSYM to the Hopf algebra of polynomials in one variable. Okay. And what this does is the following. Let's say that you have some quasi-symmetric function here. And actually, let me put the Q in a different color, because the same is true for SYM. Okay, so let me just write it like this. So that what I'm going to write is true both for QSYM and for SYM. I have a morphism of Hopf algebras, and what it does is that it takes a function which might be symmetric or only quasi-symmetric, and it gives me a polynomial, which maybe I'll call P f of x, such that if I want to know what P f of an integer, of a positive integer is, then all I have to do is take my quasi-symmetric function and plug in n of the variables to equal 1 and the rest equal to 0. So here I have my my first n variables, I'm going to plug in 1, and the other ones are going to be 0. Okay? So, yeah?
What happens if you have something positive?
We'll see. But so far, okay. So let's think about this, and maybe this is a little bit familiar to some of you. I'm going to define a polynomial. Okay, that's what I want to do. Given a quasi-symmetric function or a symmetric function, I want to define a polynomial. And the way that I'm doing it is that I'm just telling you what pf of 1 is, what pf of 2 is, what pf of 3 is, etc. Okay, I'm just telling you the value of the polynomial at the integers. I'm telling you that the value of the polynomial at n is obtained by taking your quasi-symmetric function and plugging in n of the variables equal to 1 and the rest to 0. Okay? And so then you just get some values when you plug in for the different values of n. And my claim is that there is a polynomial that matches those values. Okay? There's a unique polynomial that matches those values. And that's the one that I'm going to call pf. Okay? And Stephen's question is, okay, what happens if n is not a natural number? Well, this doesn't tell us anything. At least yet. Right? I'm only defining it for the natural numbers, and I'm claiming that it can be extended to a polynomial. And that is a morphism of Hopf algebras. Okay. Maybe it's worth doing an example of this so that we see what this looks like. Let's say that our function is the nth elementary symmetric function. So remember, this is just the sum of over I1 different from I2 different from In of xi1, xi2 up to xin. Okay, so it's the sum of all the m products of the xi's that are different from each other. Okay. So let's go ahead and try to plug in pf of k. Actually, let me instead, since I used n here, let me use k here. And let's figure out what pf of n is. Okay. So pf of n, what I get is this. I'm supposed to take this expression and plug in first n variables equal to 1 and the rest to 0. So what happens when I plug in a bunch of 1s and a bunch of 0s here? Well, the answer is either going to be 1 or 0, right? So when is it 1? The answer is going to be 1 if all of the factors are equal to 1. In other words, if I1 up to ik are less than or equal to n, right? Because x1 up to xn are the variables that are equal to 1. But if I have any higher variable, then I'm going to get a factor of 0, and so I get this. Okay? So I just get a bunch of 1s. Now, how many 1s are there? Right, so I need to choose between the numbers, from the numbers between 1 and n, I need to choose k different 1s. And so the number of ways of doing that is n choose k. Okay. For any natural number n. Now, from what I'm doing here, it shouldn't be obvious that the answer is going to be a polynomial in n. I hope that's not obvious to you from the way we're computing it here. But is this a polynomial in n? Well, it is if we write it as n times n minus 1 times n minus 2 up to n minus k plus 1 over k factorial, right? K is a fixed number. And so this is a polynomial in n of degree k. Okay? So that's okay. So that's an example of how this works, and the claim is that this works for any f. Okay. Any questions about it? Now, Stephen was asking whether there's a reciprocity law here. What if I plug in minus n? And the point is that it doesn't make sense. Here, it doesn't make sense to plug in minus n, right? Because you can't set minus n of the variables equal to 0. Okay? That seems like a nonsense thing to do, to plug in a negative value into this. But it is a polynomial, and nobody can stop you from plugging in a negative value to a polynomial. And you might know that when you plug in a negative value into here, then this is something that has a combinatorial interpretation. Minus n choose k actually counts multi-sets of size k instead of counting sets of size k. Okay. And so we'll say a little bit more about that in a minute, but for now I just want to make sure that this is clear. Okay.
And the e's form a basis, right? So presumably we can argue some proof that everything's a polynomial by just expressing it in the basis of each now.
That's right. So because I'm doing it for QSYM, for SIM, I guess. The e's the e's generate SIM, and so if ek gave you a polynomial, then you can argue that because the ek's generate all of SIM, then this is actually an algebra map, which you have to check. That gives you a proof that this is actually a polynomial. And so that's one of the possible proofs. There are several possible proofs. Okay, but I think instead of getting into too many proofs today, what I want to show you today is how this works. I mean, what this can actually give us, and we get a corollary that for any combinatorial Hopf algebra, we get a morphism from H to polynomials. There's a canonical morphism. This is supposed to be a Hopf algebra, so I've been using this H for the H. So you have a morphism from H to polynomials. Okay. Why is that? Well, because we have two morphisms in the left two boards, in the left and the middle board, and when you compose them, we get this one, right? So we can map from H to QSYM using the combinatorial Hopf algebra structure, and then we can use this natural morphism to map to K of X. Okay. So proof, just compose H to QSYM to K of X. Okay? Now, you should notice that the morphism is not a morphism of combinatorial Hopf algebras, but it actually depends on alpha. Right? You don't see alpha anywhere here. How does this depend on alpha? Well, from here to here, this depends on alpha, right? Here we're taking the morphism from H alpha to QSYM theta Q, and then we forget about alpha and we just apply this one. Okay? And so we get a canonical morphism like this that depends on alpha. I should say you've probably seen the word canonical before in other classes, and maybe you were a little bit confused by it. And canonical, when I say canonical here, I just mean you kind of didn't have a choice. I'm not being clever here. It's just that the setup gives you this. Okay, and this is the morphism that I get. Okay, so let's think about this now. What does that mean? We know many combinatorial Hopf algebras, and what we get here is a canonical recipe that, given any of those things that we can make Hopf algebras out of, we get a polynomial. And so this, I hope, excites you, because then that means we can do this for anything, right? We can do it for graphs. So for a graph, we get a polynomial. We can do it for matroids. For matroid, you get a polynomial. You can do it for posets. For a poset, you get a polynomial. And these polynomials, hopefully, give you interesting information about the combinatorial structures. Okay? So that's our goal. Our goal with this. Now, let me actually write down what the morphism looks like. So given an element of the Hopf algebra, I'm going to obtain a polynomial, which I'm going to call chi h. Okay? And remember, I gave you explicit formulas for both of these morphisms, and so that means that we have an explicit formula for this one also. And I'm just going to write it down for you. Well, actually, we don't have an exact formula for the polynomial itself, but we have a formula for what happens when we evaluate at n. Okay? Because we have a full formula for that one, and we have a formula for evaluating an integer here. If you just unravel the definitions, you'll see that this polynomial evaluated at a positive integer, at a natural number, n, is going to give you the sum. So in Sweetler notation, what you're going to do is you're just going to apply the nth coproduct and apply alpha to each coordinate. Okay, so if you apply the nth coproduct, this is going to give you h of 1, h of 2, up to h of n tensored. But now we're going to basically take away the tensor and apply alpha to each coordinate, and we're going to get this. Okay? A very explicit formula. And by the way, I sort of mentioned this last time, that this is nothing but, I mean, this is just the convolution product of alpha with itself, right? So this is really just alpha to the n, evaluated at h, convolution product. Okay. And so even if you got lost somewhere along the way, this is a great place to start again, because the point is that if you know how to take coproducts, which we do for all of these things that we have been studying, if you know how to take coproducts and if you know what alpha does, then you know what your polynomial is. And you can just compute it and see what you get. So let's do that for a couple of examples. And I think I'm not going to need any of this other stuff anymore. Okay, so, well, since I have this written here, why don't we start with this one? So example 1. We have a Hopf algebra of graphs. We have our character. That means we get for any element of my Hopf algebra, and here the generators are graphs. So for any graph G, I get a polynomial. And that polynomial is going to be given by that equation over there. Okay. Now here you might actually try to get ahead of yourself and try to guess what you're going to get. I have a graph. I get a polynomial out of it. Do you know any polynomials that come from graphs? So one is the chromatic polynomial. Maybe some of you know if you've taken some combinatorics class. Is there another one that you can think of? It's not a polynomial. But if you remember the short homework one, you computed a polynomial from a graph, the characteristic polynomial. So what you did is you took a graph, then you constructed the lattice of flats, you took the Mobius function, and then you did some operation and got a polynomial out of it, which we call the characteristic polynomial. Okay? So we might hope that is one of the two, right? If we know two polynomials, and this seems natural enough, then if we're lucky, this is going to be it. Let's compute. So chi g of n. So we're supposed to take the nth coproduct. Okay. Now, actually, let me just do this very schematically. So, what is the coproduct delta of g? So think about having g over here, and what does the coproduct do? Remember, what it does is that it just takes a subset of the vertices and it just splits this into two parts. Okay, so maybe you pick these vertices to be w, and then you look at the other vertices, b minus w, and then you restrict to this, tensor restrict to this. And so you can actually just think of the coproduct as just taking this and a graph and splitting it in two. And let's actually just call this, in Sweetler notation, you would call this G1 and G2. Right? Okay. So that is the first coproduct. So what happens if we now take the nth coproduct, or I guess the n minus first coproduct? We know what that does is that instead of cutting my graph into two parts, I cut it into n parts. Right? So I take my graph, and now I split my set of vertices into n sets. Okay. So maybe this is one set, first coordinate, then maybe this is another set, second coordinate, and so on. Until the coordinate. Okay. That's what the nth coproduct does. Okay. And so let me actually just draw that picture here, taking my graph G and splitting it into little graphs. Okay. And each piece is called GI. Now, what am I supposed to do? I'm supposed to do alpha of G1, alpha of G2, alpha of etc. Right? So let's figure out what that is. And again, very often, because the characters that we choose are pretty trivial, that means that this computation is not very hard to do and the answer is fairly simple. We get the sum over this partition, all the different ways of cutting our graphs into different parts. And then what is this going to be? Well, it's going to be either 1 or 0, because you're multiplying a bunch of 1s and a bunch of 0s. When is it 1? If each Gi, what did I call it? G sub I has no edges. Right? If Gi has no edges, then alpha is equal to 1. But as soon as I have one edge in any of these small blue graphs, I'm in this situation, and this multiplication is 0. Okay. So what am I doing here? If you look at this differently, I'm taking my graph, and I'm cutting the vertex set into n pieces. So really all I have is a function from the vertex set to the numbers from 1 up to n. For each vertex, tell me what piece you're in. Right? So in other words, I map these vertices to the number I. But now let's stop calling them numbers, let's call them colors. Right? So when is it true that each GI has no edges? It's true when you never color two adjacent vertices with the same I. Okay. So in other words, what this is 1 if you never have, let's say, vertices A and B with the same color, and 0 otherwise. But you see, we gave this a name last time. This is precisely what's called a proper coloring of the graph. You color the vertices so that no two adjacent vertices have the same color. And so this is precisely the number of proper colorings of the vertex set. Okay? And this is precisely what's called the chromatic polynomial. Okay? Yep.
What if we were to go through SIM instead of QSYM? Get the other
Actually, if you're, so the question is, what if I go through SIM through QSYM instead of going through SIM? And the answer is that if you're co-commutative, then actually you're going through both at the same time. It's the same thing to go through SIM or through QSYM. Now, I don't know. Who has studied the chromatic polynomial before? Maybe some of you have seen it, maybe some of you haven't. Okay. So let's think about this now from scratch. Okay. So I think some of you know and love this polynomial, and some of you maybe are seeing it for the first time. You have a, and by the way, where does this come from? This comes from map coloring, where really you have a country. Okay. It's kind of like what Colombia looks like. It's my bias right there. And then you have a bunch of different states. Okay, I don't know. I'm not going to draw them all. They're called departments in Colombia. And you want to color this map. Okay, so you want to give a color to each department, to each state. Now, you don't really want to use a different color for every state because it's going to look really tacky. And if you look at any map, of any real map, they never use a different color for every country. You want to repeat some colors, okay? And so you could actually just, color this guy blue. But the thing is that if you color this guy blue, then you don't want to color the neighbors blue because you would get confused. Okay? And so you can color maybe this one blue, this one blue, this one blue, etc. Okay. And, well, we have what's called a dual graph, which tells me what are the adjacent things. Right? So if I put a vertex inside each state and an edge between neighbor states, then a proper coloring of the graph is precisely a proper coloring of the map. You don't want to color two neighbors of the same color because you wouldn't be able to tell them apart. And so that's where this comes from. And that's why these are called proper colorings. And that is why we think of these as colorings, because they really like coloring the map. And so chi g of n is the number of proper colorings if you happen to have n colors in your hand. Okay? Now, the first time that you see this, you should be very surprised that this is a polynomial, right? Because I'm saying, okay, if you have 10 colors, how many ways do you have of coloring this? Or if you have 20 colors, or if you have 30 colors, and those are just some numbers. But it turns out that actually that's a polynomial function. Okay? So if you want to know how many colorings there are with n colors, that's actually a polynomial in n. Okay? And that's maybe the first theorem about this, and that's why this is called a chromatic polynomial, even though it's not obvious at first that it's a polynomial. Okay? But it's a polynomial because it comes from this, right? It lives in the Hopf algebra of polynomials, therefore it better be a polynomial. So this is kind of a high-powered way of saying that it is a polynomial, but it is one way. And it also proves to you the inevitability of this polynomial, because people always say, oh, in history, combinatorics used to be considered kind of a toy field where people were just having fun and coloring maps and doing irrelevant things like that. And so, I don't know, maybe the first papers on this topic were considered very recreational, and okay, who cares about your coloring of your maps? This is not real mathematics, This is not manly mathematics. This is kind of the vocabulary people used to use, actually. I've heard people talk like this. People are stopping, fortunately. But somehow the point is that if you build this whole machinery, then this polynomial just comes out inevitably. Okay, and it's just the one that comes out. It's not anything clever that we did. It just we tried to see what it was, and that's what came out. Okay? And so that shows some kind of one reason why this is very natural, also from this very algebraic point of view, and not just from coloring maps. Okay. Okay. So that's one thing. But actually, let me give you a theorem, which also comes straight out of the theory, and you have to kind of unravel the definitions to see this, but the theorem is the following, that the chromatic polynomial of a graph is actually the same as the characteristic polynomial. Almost. The only difference is a factor of q. So this is the one you computed in your homework. And this is something about coloring graphs. And they actually are the same thing, even though they're constructed in very different ways. Okay. And maybe this shouldn't be too surprising at this point, because we already encountered this in the Hopf algebra context. And so the point is that if you kind of unravel where we encountered it, you'll see that the place we encountered it is exactly the same as this thing. Okay. And so this is a corollary of all this framework. Okay. So this is the chromatic polynomial, and this is the characteristic polynomial. And that means that there was a much easier way of doing the homework problem, right? I asked you to find the characteristic polynomial of this graph. Well, let's compute it. How many colorings are there of this graph that are proper? Let's say that you have 2 colors. Well, here it doesn't really matter. You can choose any color, right? So you have Q. I'm computing the chromatic polynomial. So here you choose any color. Here, how many possibilities do you have? You can choose any color except the one that you just chose. So first choice, there's this many. Second choice, there's this many. How many colors do you have available here? Q minus 1, because you have to make sure not to use the same one you just used, but it's okay to use this one again. And how many choices do I have for this one? Well, these 2 colors are forbidden, and they're different from each other because they're neighbors, right? So these 2 are forbidden, everything else is okay. So Q minus 2. Okay. So what was the answer to your homework problem? It's just Q minus 1, Q minus 1, Q minus 2. I don't know if any of you noticed that that's polynomial factored. And it factors really nicely, and this is the reason. So that's the kind of these are the kind of combinatorial statements that just come out of the theory. Okay, so we're doing Hopf algebra theory, and then when you map it to polynomials, then we get some results. Let me do a different example. So let's see. I think I can. Let's do example 2. Let's do it for posets. Actually, let me, before I say this, before I say this, let me say a couple more things that are interesting about this polynomial. Does anybody remember offhand what the answer was here? I wrote it down somewhere. So, okay, so Q was this extra factor that you didn't have, and then the characteristic polynomial that you guys computed in the homework was this one. So, and another thing that we like to do in combinatorics, whenever you see something like this, whenever combinatorialists see a positive integer, they want it to count something. Or to at least, yeah. So, so here, for example, we might say, what are these numbers 1, 4, 5, and 5 and 2? Or what can we say about them? And so here's an old theorem that is not hard to prove. Proposition. The coefficients of this polynomial alternate in sign. That's an old result. I forget who proved it. And it comes from the fact that actually you can give a recursion for how to compute these polynomials. And when you write the correct recursion, then this becomes pretty trivial by induction. And so we know that the signs go plus, minus, and then we can look at those numbers and say, what can we say about those numbers? And people computed a lot of those polynomials, and they made the following observation. So this was a conjecture originally of Reed and Rhoda. In 1968. The conjecture was that if you look at these numbers, they increase and then decrease. So this one goes 1, 4, 5, 2. And they computed lots of examples, and they observed that in every single example this was true. The coefficients of this polynomial are what's called unimodal, meaning that they first increase. Let's do it in a picture. In absolute value, yeah. So we start with a small one, then increase, and then start decreasing. But it doesn't. It first goes up and then it goes down. Okay. And one trouble with proving this conjecture is that people didn't really know what those numbers counted or what they were, and so it's been kind of a mystery for a while. But I think one of the most exciting news in combinatorics in the last couple of years is that this just became a theorem last year. So this is now a theorem due to Jun Hu. Actually, He is how you say his name. So what June did actually is that he managed to understand what these numbers are, at least one interpretation of these numbers. And it turned out that the interpretation is that they're Miller numbers of some hypersurface. It's a really beautiful but kind of intricate explanation in algebraic geometry. And if you know some tropical geometry, there is a way of saying in tropical geometry terms what these numbers are. Okay? And by understanding what they are, he managed to prove this conjecture. Actually, I think some of you met June because he was here earlier this semester, and he gave a talk about this. And it's pretty cool because he actually did this as a first-year PhD student, and he just solved one of the most important open problems in the field. Which I often think that sometimes young people don't know how hard things are supposed to be, and then they just do them. I think those of us that have thought about them for a long time maybe are convinced that they're harder than they really are. Now, don't get me wrong. His proof is really beautiful and really original and really clever, and also uses a lot of high-powered mathematics. But yeah, I like that it's a very young person that just did this. Anyway, so I just wanted to mention that to kind of, I keep wanting to make the point very clear to you that all of this is very alive and happening today. Okay, so maybe what I want to do is, instead of trying to, so this was the example 1 of graphs. I was going to do an example 2 about posets. You can apply the same framework to posets, and then you're going to get a parallel theory of a certain polynomial assigned to a poset, and in this case, you get something called the order polynomial of the poset. I think those of you that like order polytopes and things like this should look into this. But I think maybe because I don't want to rush anything, and so I wrote a little bit on the notes, and if you're curious about that, I can tell you more. But this just gives you a prototype of what the theory kind of looks like. And instead of going to posets, let's come back to graphs and just prove one more theorem about this. So the next thing I want to do is answer Stephen's question about combinatorial reciprocity. So here's a proposition. Which we might call reciprocity. Okay, so the setup is this. We have our Hopf algebra mapping to polynomials, right? But the way we're defining this, actually, we're only saying what this function does. So given an element of the Hopf algebra, we are saying what was the notation that I used? Chi h of n is, okay, for n a natural number. Okay. So in principle, we only define this for natural numbers, and then we said that that's a polynomial. And as combinatorialists like to do in this situation, we're stubborn, and we try to plug in a negative value and see if we get something interesting. So what happens if you take this polynomial, which in principle we defined for positive integers? What if we plug in a negative integer? Now, if you're used to these kind of combinatorial reciprocity theorems, usually what this says is that even though you plug in nonsense, if you plug in something that shouldn't work, it turns out that the answer is something combinatorial that makes perfect sense and counts something. And it turns out that that happens here. It turns out that this thing, which is nonsense, I mean, it's not nonsense, but it doesn't. We have no idea what it means to plug in minus n. It turns out that what we do is just plug in n, except for the antipode. The antipode is this kind of inverse thing that we have. And it beautifully commutes with this. Okay? So if you want to know what plugging into a negative value is, you just go to the antipode and see what the positive value is. Okay? The proof of this actually is very simple, because this is a morphism of Hopf algebras. Right? Now, if it's a morphism of Hopf algebras, then it has to preserve the antipode. Meaning that we have the antipode from H to H. We have the antipode from K of X to K of X. Okay. And so this diagram has to commute if this is supposed to be a morphism of Hopf algebras, right? And if you look at what this says, okay, what do we get when we go this way? You go to from H, we go to S of H, and then we apply chi. So we get chi of SH. Right? That's what happens if we go in this direction. What happens if we go in this direction? You start with H, you go to chi of H, and then you apply the antipode of polynomials. Do you remember what the antipode of polynomials is? You can go. You can guess it. It just takes a polynomial x. I mean, here we go from H to K, H of X. And if you look back, we computed this antipode. It's very easy, and all it does is it changes x to minus x. And so this actually sends me to chi h of minus x. That's what the antipode does there. Okay? And so by the transfer of the antipode, these two things have to be equal to each other. Okay? That's it. So this is the reciprocity theorem. Okay. And let me give you one particular case, which is that if I plug in minus 1, then I get chi of S of H evaluated at 1. Okay. But what is chi at 1? Remember that chi at n is applying the nth coproduct and then applying alpha to each term. So 1 is applying no coproduct and applying alpha to it. This is nothing else but alpha of S of H. Okay. So this is pretty simple. And that's a general reciprocity theorem about Hopf algebras, which again we can apply to any of our favorite Hopf algebras. And given that we're doing this in such detail, why don't we apply it here? So for H, the Hopf algebra, I don't know why I just erased this, Hopf algebra of graphs, the co-commutative, alpha of H, alpha of a graph is 1 if the graph has no edges, and it's 0 otherwise. I want to know what I get when I apply chi, when I evaluate chi at minus 1. I'm going to prove a theorem. This is equal to something. Okay? And let's just write the proof, and then we'll figure out what the theorem is. So, what is it? Chi g of minus 1 is applying alpha to S of g. Now here's where you hope that you've understood this Hopf algebra well. Alpha is easy. Alpha is just this. Do we know what S of g is? Do we know what the antipode is here? there are some things that I've planned to develop from beginning to end of the class, and actually this is one of your homework problems, was precisely to find the antipode of this. And the answer to that homework problem, the antipode of graphs, was the following thing. I'll write it down and hopefully it looks familiar. What you do is that you sum over the flats of the graph. Then we get minus 1 to the number of vertices minus the rank of the flat. Then we got the number of acyclic orientations of G contract F. And then we got G restricted to F. I hope this looks vaguely familiar. I know it's been a little while. And there's a bunch of things to parse here. Okay? So, flat, okay, we'll remind ourselves what that is in a second. A stands for acyclic orientation. And we'll also remind ourselves what that means in a second. And G restricted to F is just the restriction. Now, this might look very complicated, but if you think about it, again, the point is that alpha is pretty brutal. Alpha kills almost everything. The only things that alpha doesn't kill are the things that don't have edges. What kind of restriction? I mean, these are numbers, right? Alpha is the function. These are just constants. And this is the graph. Really, what I'm doing is applying alpha of the graph. Now, when is alpha of the graph not 0? Well, we need this restriction, G restricted to F, to have no edges. How often do you have a restriction that has no edges? You have your whole graph, and you want to restrict to a part of the graph that has no edges. Sorry, remember that F is actually a set of edges. Okay, that makes my point even more eloquently. I have a graph. I look at a set of edges, and I restrict to those edges. And I want the result to have no edges. How can that happen? The only thing is if I restrict it to nothing. Right? Everything else is killed by alpha. So this is, no matter what all these symbols mean, they're always 0 except if F is empty. So let's just figure out what happens if F is empty. Flat, it doesn't matter what it means, it's just empty. Minus 1 to the V, the rank of empty must be 0. No matter what rank was. If it's empty, it better have rank 0. So we get minus 1 to the number of vertices. G contract empty set. No matter what contraction meant, if you're contracting empty set, you must not be doing anything. And alpha of this is 1. And so here's the theorem. When you take the chromatic polynomial, which counts colorings, and you plug in minus 1, which is like saying how many colorings do I have with minus 1 colors, that shouldn't make any sense, right? But it turns out that you actually get this answer, minus 1 to the number of vertices times the number of acyclic orientations of the graph. So it's some other combinatorial problem, and for some reason these are related by some kind of duality, colorings and acyclic orientations. Yeah. So what are acyclic orientations? Otherwise it's hard to get excited about this theorem. Let me leave this here because this is important. And actually, let me leave this example because then we can use it as a test case. So recall that an acyclic orientation of my graph is an assignment of directions to the edges which produces no cycles. So for every edge, you decide whether it goes this way or that way, but you want to make sure that there's no directed cycles. So let's figure out, for example, what does an acyclic orientation of this guy look like? Let's say that I start, what should I orient this edge? This doesn't matter because no matter which way I orient it, this is not going to form a cycle. So either I orient it like this or the other way, it doesn't matter. Which way should I orient this one? Well, I don't know. So far, it doesn't matter. Maybe I'll orient this one this way. Now here I have to be smart because I can't close this cycle. Right? So if I orient this guy this way, I can't orient this guy this way. I have to orient it this way. So this is an example of an acyclic orientation. So how many acyclic orientations does this graph have? 12. How are you computing that number?
Well, so I see in the triangle, you're going to have two directions that are the same and one that's different. So you just pick the one that's different. There's three choices there. You pick a direction on one that's different. So there's two choices there. So that's 6 ways to do the triangle. And then there's 2 things you can do with the lone edge.
Right. So basically, there's kind of 2 independent things you need to do here. Figure out what this edge does and what the cycle does. So how many ways do you have of orienting this edge? 2. Either this way or this way, it doesn't matter. What about this cycle? How many ways do you have of orienting it? Well, the total number of orientations, acyclic or not, is 2 times 2 times 2. 2 cubed. There's 8 total orientations. How many are bad? This one and this one. 2. So the remaining 6 are okay. So A of this is 12. Okay. Now, the point is we didn't need to be this smart. What did we need to do? It would have been easier to just say, okay, we'll plug in q equals -1 here. That means just add up the coefficients. 1 plus 4, 5, plus 5, 10, plus 2, 12. And that's what the theorem says, that the number of acyclic orientations is what you get when you add up the coefficients. I say add up the coefficients because these coefficients alternate in sign. And so when you put -1 cubed, you're going to get -1, -4, -5, -2. The signs are going to line up perfectly. Okay. And so the number of acyclic orientations is just adding up the coefficients of the chromatic polynomial in an absolute value. Okay. This was actually probably the theorem that got started, or at least one of the theorems that got started in this kind of subfield of combinatorial reciprocity. And now we know in combinatorics a lot of polynomials that seem to be defined only for positive integers, but then when we define them for negative integers, we get an answer that makes sense, but it's an answer to a different problem. So it's a theorem of, this is an old theorem of Stanley, and it kind of gave rise to several other theorems in this vein. But the point that I want to convey is that if you're willing to put the work and learn about Hopf algebras, then this is just a recipe to make theorems and publish them. It's not quite like that. You don't want to publish 10 different papers using 10 different versions of this, but really you can apply this to any Hopf algebra that you like, and in some cases the answers that you get are very interesting. In some cases they recover old theorems, and in some cases you get some new theorems that we didn't know. Okay. I think that's all I'm going to say. There's really, I mean, I hope you get the feeling that even though we just spent a semester talking about Hopf algebras and combinatorics, we really have only begun to scratch the surface. And that's always intimidating and exciting about mathematics, that you can spend a whole semester and you realize that you learned this much. And maybe by spending another semester, you're going to learn another bit. Okay? But I hope this gave you a little bit of a flavor of kind of what the algebraic theory of Hopf algebras is, what combinatorics can do to help that theory, and what that theory can do to help combinatorics, and have a fruitful exchange between the two. And I think that's where I'm going to stop. So that'll be the end of the course, and I hope you get excited to learn more about this stuff later on. Okay. Thank you, guys. Now, okay, I guess you guys know the drill better than me for this. Can I get a volunteer? Are you volunteering? Okay. Krista's going to volunteer. So I'm going to pass these around. Now, I think mathematicians more than anybody know that numbers are nice, but really it's more helpful to say more than numbers. So, I mean, you're supposed to put numbers here, and that's fine, but I'm more interested in what feedback you might have as to, you know, what worked well in this class, what could be improved, what we should keep, what helped a lot, what kinds of things could be done a little bit differently, etc. So please take the time to write the most thorough comments you can. I actually didn't have pencils here. So make sure to draw the bubbles in pencils, and everything else is probably fine. So maybe borrow from your neighbor for the bubbles part. And I'll write down some information here. I guess I can turn the microphone now. Okay.